Alright, in this video we're going to deal with rationalizing radicals. Now, this occurs when we have an equation or an expression following the form for any p of x or any function of x in the numerator. In the denominator, you have a function which is a radical, or you can for easier visualization, we can do it this way. I'll be giving an example. Let's say we have x over the nth root of y. Alright, now x here can be any function or any number, so is y here. Now they're not necessary, they may be the same but not necessary always. Now let's consider this general form. How are we going to rationalize an expression given this? Take note, recall that y here is your radicand and n is your index. Our main goal in rationalizing is to remove the radical sign in the denominator. So, how are we going to do this? If you have this function or expression, we need to multiply 1 so as to not change the value of the expression. In this case, 1 would be written of the form the nth root of y raised to n minus 1 over the nth root of y raised to n minus 1. Any number divided by itself except 0 is always equal to 1. This gives us x, the nth root of y raised to n minus 1 all over nth root of y raised to 1 plus n minus 1. Recall the property of exponents or the laws of exponents. When you have the same base, when you multiply expressions with the same base, you add the exponents. So the exponent here is 1, the exponent here is n minus 1, y raised to 1 plus n minus 1. This gives us further x, the nth root of y raised to n minus 1 all over the nth root of y raised to n. Nth root raised to n would simply cancel out. Final answer, x nth root of y raised to n minus 1 all over y. Let's have an easier example. Let's say we have 3 over the square root of 2. You are asked to rationalize this. Again, the index here is 2. The exponent of 2, our base, is 1. So we need to multiply the square root of 2 over the square root of 2. This gives us 3, the square root of 2 over square root of 2 times 2 is 2 raised to 2. That would cancel out. 3 square root of 2 over 2. Another example. Let's say we change the index. Instead of having square root of 2, we're going to have the cube root of 2. So 3 over the cube root of 2 times, if we're going to rationalize this, we would multiply not the cube root of 2, because 2 times 2 is simply 2 raised to 2. We need 3. So again, from here, see the pattern, n minus 1. Our n is 3. So 3 minus 1 is 2. So we have 3 cube root of 2 squared over cube root of 2 raised to 3, or this can be simply written as 3 the cube root of 4 over 2. Now, another example you might encounter. Let's say we have 4x over the fourth root of 9. Let's just say 9y. The fourth root of 9y. In order to rationalize this, there are two possible ways. One, we can first find the base of 9, expressing it in terms of lower prime numbers, or we can just simply have it as 9 and then reduce it later on. If we're going to choose the path of having this reduced to lower prime numbers, 9 is, recall, 3 squared. So, if we write it, 4x over 4 root of 3 squared y. Now, we can rationalize. So, we multiply the fourth root of 3 squared by 3 squared. Again, 4 minus 2 is 2. And then 4 minus 1. So we have y raised to 3. Fourth root of 3 squared y cubed. This gives us 4x, the fourth root of 9y cubed over 3y. The same problem, but we're not going to transform 9 into its prime roots. Instead, we're going to have it simply as 9 and proceed with rationalization right away. We multiply fourth root of 9 raised to 3 y raised to 3 over fourth root of 9 cube y cubed. This would give us 4x, the fourth root of, so 9 raised to 3 is 729. Y raised to 3 over 9y. But the problem is 729, the fourth root of 729, we can still further simplify it. 729 is 81 times 9. So this would give us 4x, the fourth root of 81 times 9 y raised to 3 over 9y. The fourth root of 81 is 3. So 4x times 3, fourth root of 9y cubed over 9y. That cancels out. We are left with 3. Final answer, 4x, fourth root of 9y raised to 3 over 3. So, there's nothing wrong with either path, but sometimes this leads to a longer one. You would still arrive at the correct solution at the end, but the path is longer. This takes more time to think of because you have to convert, but it ends with the simplest form immediately. Alright, another thing to consider when we talk about rationalizing radicals is when you have a sum or a difference in the denominator. So, let's say we have 3 plus square root of x over the square root of x minus 2. Now, what we need to multiply here is the conjugate of the denominator. Since our denominator is the square root of x minus 2, its conjugate is the square root of x plus 2 and square root over the square root of x plus 2. So this term, this is our denominator. The conjugate is this, from minus to plus. If this is plus, this should have been minus. Right? Now, this works off from the principle that x plus y times x minus y gives us x squared minus y squared. If you're going to notice, we only end up with two terms. Recall also that x plus y times x plus y gives us x squared plus 2xy plus y squared. So if we're going to use the same operation, if this is plus and we use plus, we end up with a middle term. In this case, it would still have the radical sign, which is what I'm trying to avoid. So we have to follow this pattern. That's why we need to multiply the conjugate. Now, from here, again, you can simply use your FOIL method. So that gives us 3, the square root of x, plus 6, plus the square root of x squared, plus 2 square root of x. Alright, so first term, second term, third term, last term, divided by, alright, so we have the square root of x squared. Just to show that it would end up with this, we are going to use the FOIL method first, plus 2 square root of x minus 2 square root of x minus 4. That gives us, alright, can combine similar terms, 3 plus 2, that gives us 5, this is x, so x plus 5 square root of x plus 6 over square root of x squared, get x, plus 2 minus 2, that is 0, minus 4. That's your final answer. Again, you cannot cancel x and x here because of the presence of the addition and subtraction symbols. Please make sure to avoid those errors. Okay, so that's the end of the video for rationalizing radicals.